Okay, uh, let us start. So I'll share the screen. Okay, so today is our sixth discussion So we'll try to recap what we have learned in reactions of alkene, and we'll proceed towards alkynes, and then we'll discuss some of the questions. So reaction of alkenes and further alkynes, right? So what we have studied till now is, so suppose this is an alkene, and then whatever you have studied till now is how they can react with different reactants, particularly in addition reactions. You can react with a hydrogen halide as well as react with a hydronium ion to give you hydroxylated product. Then you can react it with any non-polar, okay, like bromine, chlorine in DCM or CCl4 kind of solvents. Then what you will get vicinal dihalide and with anti-addition, right? So it will be like this. Okay, these are anti-addition. Similarly, we studied addition of bromine in presence of water, where water is in excess. So what will happen? This is also an anti-addition. So first bromine will come, and then water will add. The second step, water will add. So this is also anti-addition. Now, apart from this preliminary reactions, we have few different reactions where you can control the stereo or the reduced selectivity, right? So today we'll discuss some of them. So first of them is called oxymercuration, demercuration reaction. Okay, why it is important? Because you see, so we discussed in the previous class that if you do reaction with hydronium ion in this case, what you will get actually, it will be, okay, there will be some rearrangement, and you will get finally the most stable product. But this position you cannot get your substitution, okay? But if you use another way, if you use mercuric acetate, and then in the second step, this is step 1, this is step 2, if you use NaBH for a reducing agent, what you end up with is this. Okay, this is your desired product. Okay, so here no chance of rearrangement. Okay, that is why people use this oxymercuration demercuration reaction. But The negative thing is that mercury is toxic. Okay, so it is not recommended to use in the lab, but still, if you don't have any other option, then you can go for this reaction in a controlled way. Okay, so similarly, we'll study some other reactions. One of the most important reaction is hydroboration. So hydroboration reaction. So what the name suggests, so you will have a boron containing component, and you will also have hydroxy or hydroxy group containing component. So both these are associated in the reaction mechanism. So what is the general scheme of the reaction? Suppose you have an alkene, and you will there are two steps. First, you will react it with BH3 or any boron, alkyl substituted boron, and second step you have to react with H2O2 to get your hydroxylated product. So how the reaction goes on is like that. So the product here would be this, and the mechanism. So BH3 is electron deficient, right? So this is electron deficient. Okay, so it has a pi orbital which is vacant. So this electron density from your alkene, it can look for the empty pi orbital of boron. Okay, and then what will happen, this bond between boron and hydrogen, so this will get weak. Okay, this will get weak, and it will try to go here. Why it will go here? Why not the other way? Because if you see from the first step, this is H, this is H, this is another H. So when it is forming the bond with boron, then you will have a positive charge here. But positive charge in secondary place is more stable than 1 degree carbocation. Okay, so that is why this will be the major product, and you will have, so your intermediate will look like, intermediate will be BH2 or Br2 if you have substitution. Hydrogen is here, and now you are giving H2O2 in presence of a base. Okay, so that will convert this boron, that will convert this one to a stable other boron compound, and then you will get your desired hydroxy compound. Okay, so how the stereochemistry looks like. So let us discuss one reaction. BH3 PHF. So as these boron compounds are so much reactive, they are kept in THF or ether or anywhere. Okay, so how so this is THF, you have a oxygen lone pair. Hmm. So this this boron, which has electron deficient nature and empty pi orbital, so this one try to go to form an adduct. Okay, these are called Lewis acid. Lewis acid. So this will go and form a adduct. Okay, these are stable. This is just to stabilize your boron, electron deficient boron compound. So now if we go to the reaction, so your double bond will be going to here, B H2, and then this H. So it will form bond. Okay. So once you know that it is a concerted addition, concerted addition. Okay, it is a one step actually. So you see that if it is concerted, then from the same side it will attach. Okay. So this is scene addition. If it was in the two step process, then what will happen in the intermediate? So yeah, this is the intermediate. So as this is a concerted process, then it will come from the same side. It cannot, go to the other side and attack from there. Okay, from the same side it has to attack. So that is why the product uh, relative geometry will look like. Suppose you have the methyl group here, you have the proton here, and you have your OH here. This is one case, or else what can happen? This is the opposite isomer. Methyl is on the top, proton is on the bottom, and OH is also on the bottom. So these two can be formed. Okay, so these we generally call as regioselective product. Okay, so to know that the reason behind your alkene that is attacking the electron deficient boron center, why it is this way? So the reasons are reasons for the selectivity. First reason is steric factor. Okay, first reason is the steric factor. So you have a larger substituent on boron atom, suppose BHR2. Okay, so these are can be very large. So prefer to bind the less sterically steric site. Okay. Second point is electronic effect or electronic factor, or which is stability of which is stability of 2-degree carbocation, then terminal 1-degree carbocation. Okay, so let us move to our next reaction, which is another syn reaction, which is called osmium tetroxide oxidation. This is also regioselective. scene addition. Okay, so how the reaction goes, you have a alkene, you react it with osmium tetroxide. Okay, now if you see, this one can bind with two of the oxygen atoms from the tetroxide. So it will look like either this one uh, or from the other side. Now you have to treat with sodium bisulfate and you will get the product. Okay, so this is also one kind of scene addition or radioselective addition. Now next reaction is ozonolysis. So very very common or famous reaction. Okay, that people have practiced throughout decades or centuries. So in ozonolysis, what you do, you react with O3, that is ozone. This is the first step, and then you have another step. So what it will form? It will break the double bond and it will form two carbonyl compounds. In this case, two ketone. In these two. Hmm. And what is the intermediate? So intermediate, you can draw it like this. Okay, and then you react with dimethyl sulfide. Okay, it breaks like this. Then you get two ketone. So uh, you can change this reactant in the second step to some other reactant or other reactive reactant or some oxidizer. So suppose you have this one. Okay, now what you are doing, you are first reacting with O3 and in the second step you are adding one oxidizer H2O2. What will happen in the first step? This is similar. This is okay. Uh, just a second. It will not be look like this. Yeah, it should look like this. Now, now what will happen here? So you have the traditional breakage upon. So it seems that in this part there should be one aldehyde forming, but if you have added one oxidizer in the second step, so all these things will be oxidized. So this one, the left part, will convert to an acid, that will be CH3, CO, OH, and the other part ketone will remain like the same. Okay, because it cannot oxidize to the acid. Okay, after, because it doesn't have any proton or something. Okay, it will stay like this, but it will oxidize to the acid. So this is one thing you have to remember. Then pretty basic thing, but which is catalytic hydrogenation. This we all have studied. Okay, if you have an alkene and if you use some metal, means platinum, palladium, nickel, okay, even activated carbon, and if you use hydrogen gas, H2, what will happen? This H2 molecule will be, you know, uh, anchored or adsorbed in the surface of the metal, and then you can have your alkene. Okay, R2C, Cr2, R2C, Cr2. So that will come and take the hydrogen and go. So in this case also, it will have a scene addition. So this will be a simultaneous addition. So that you will end up with the regioselective product. So it will look like, okay, like this. So in this case, reactivity of alkenes depend on the substitution. Okay, if you have uh, less substituted alkene, they will react faster, without much energy requirement. If you have more substituted alkene, reacts slower and needs more activation energy. It's nothing, just that if you have more substitution, your alkene is much more stable. So you try to imagine a reaction coordinate with energy. So this is your energy diagram, this is your reaction coordinate. So somewhere here you have the less substituted one, and here you have the more substituted one. So this is much more stable. And when it is going to the product, so suppose this is the product and this one. So this one is going through activation barrier to the transition state. This is also going through a transition state. Okay, but this difference is much more. Okay, this energy requirement is higher. It's higher, and that is why it is reacting slow, the more stable one. Okay, I guess it is easy to understand. Then, so this is one thing that was left from last class. This was HBr addition with H2O2. So we did discuss about HBr addition in you know carbon tetrachloride, DCM, this kind of solvents, in water also, but we did not discuss with H2O2 because this mechanism is different. So this is going through a radical mechanism. That is why the product that we expected in earlier cases will be completely different here. So the difference I can show you, like you have similar alkene. So this is the first case. You are reacting with HBr in normal conditions. So what will have, it will go through a carbocation step, and you know carbocation will be much more stable here. So we end up with this compound. But if the same reaction you are going to do in presence of H2O2, what will happen actually? You will get the other product. Okay, and how the reaction is going on? So you have to go through the mechanism. So this is actually the radical initiator. So what will happen? So in this molecule, if you shine light, okay, what happens? This goes through a homolytic cleavage. Homolytic cleavage is, uh, breaking of bond where the two electrons will go to two different atoms. Okay, that were involved with the bond. So each atom will get single electron. So in this case, you will have something like this. Uh, you have some levels, electronic levels in the molecular orbital, and at the extreme, HOMO, you will have single electron. So rather, it is called singly occupied molecular orbital or SOMO. Okay, so once it is generated, once radical is generated, so radical is also an active species. Okay, so this will also look for some other species to transfer the radical or to do some reaction. Okay, so most feasible will be HBr. Okay, because it is most easy to find out that proton. What will happen? It will go and take the proton, and this bond also will break and give the electron to the bromine. So Br minus radical will form. So what is happening after initiation? After initiation, your radical is propagating. Now imagine the next steps. What can happen? It can go to another HBr, or it can go to the alkene. Now it can go either here, or it can go in this case. So what you will get actually, you can get either this radical, or you can get, in this case will be bromo here, and in this case radical will be here. Now this 3-degree radical and this 1-degree radical, 3 degrees is much more stable. Okay, the same reason for that we considered that 3-degree carbocation is more stable. The same reason can be used for 3-degree radical also. Okay, the hyperfine hyperconjugation. So 3-degree radical is much more stable than 1-degree radical. So this will be the major case. So now what we know, this radical is the major, and you will have also HBr present. This radical will again abstract a proton and generate one more Br radical. So what you will have this compound plus Br radical. Now it will go on and on, okay, until your all the starting material or the alkene uh, is exhausted, or is utilized. Now the end step will be, the termination step will be, termination step will be combining of two radical. Okay, two radical can combine, so maybe you have Br dot, so it can react with another Br dot to form Br2, or it can react with this radical to form a dibromo product, right? It can also react with the which, and it can form HOBr. Okay, so many things can be possible. These are all side products, but this will be the major. Okay, now let us move to the next part. So with that, uh, alkene part is over. We move to alkyne and their reactivity, right? So think of the simple alkyne, which is acetylene or ethine. We already discussed so much about this. So you will have this linear kind of system, yeah, and then what you have, you have one sigma bond, and then 2 pi bond presence, right? See, this is the structure of just the preliminary alkene, that is acetylene. So you can go on and on to have more complicated structures, like you can vary this R group on both sides to get complicated alkenes, and you can also increase some chain length. Okay, so what are the general properties is, first one is much stronger than double bonds. Okay, so which relates that much shorter. Okay, second point is carbon atoms are sp hybridized. Third point is 2 pi bonds. Okay, and due to this pi bond, these are electron rich, acts as nucleophile, right? So we'll see this the reaction. So these are almost similar to alkene in terms of reactivity, but there are some differences. Let us start. First reaction is electrophilic addition of HCl to acetylene. Okay, so how this goes, like HCCH, and you have HCl. So we already studied for the alkenes how they reacted. So similar way, you can think of an electron density from the triple bond. It will go and attack the proton. This bond will break and it will give the electron density to the chlorine. So then what you will have here, HC. So the positive charge will be on this atom. You have a double bond. Proton will be taken by the other carbon. So this carbocation is termed as vinylic carbocation. It is not very much stable because you know that it is an sp2 hybridized. Okay, base character is much more, so it is not that much stable compared to the sp3 carbocations. Hmm. But still in this case it can work, and if you have this chlorine minus, it will go and attach here, so that you will get HCCl CH. Hmm. Now in this medium, if you have HCl excess, this can further react, right? So you can have the proton. So now there is also a chance of selectivity. So if your carbon is this one, if this carbon, the double bond is going through this way to attack, take the hydrogen, then what will happen? You will have the proton, the carbocation generated here, H, H, and H. So this position will be more stable. Why? Because Cl has minus I effect, and that is much lower compared to the plus M effect. Okay, it can also give via resonance. So that is the way it can stabilize the carbocation. So what you will have in the next step, Cl minus will come again, and you will have a geminal dihalide. Cl, Cl, and H. So this is called gem dichloride. This gas. Okay. Now, similarly, if you think of here, H, C, triple bond C, R, and if you react with two molecules of HBr, then you will end up with CH3, C, bromine, and R. This is also a gem product. The reaction mechanism is same. Now let us move further. Reaction with Br2. In this reaction with bromine, the similar fashion takes place where it was the case for the alkene. Okay, so again some bromonium ion it is forming. So you have Br. You have some electron density here, so that you can generate a polarization del plus del minus, and it will attack here. This will break. Okay, so that you will have something like this. Okay, now you have Pr minus, this can attack from the other side. Okay, and we will have the anti product. This is also stereo selective. Now if you have excess of Pr2, then this one can also react this alkene, so that you will finish with CH3, C, Br, Br, C, Br, Br, CH3. Okay, so remember where there is addition of bromine, chlorine with some triangular intermediate step. So always this will go through a stereo selective way or the anti-addition pathway. So let us move to the next one, that is hydroboration oxidation. This is similar to the alkenes. Okay, so let us see for this example. You have R2BH in THF. What will happen? You will get this compound. So now this steric factor is important. Okay, so if you use less bulky groups, the reaction will not stop in alkene stage. Okay, so you need to use some bulky group. Need to use some bulky R group, right? So generally people use this di. So for example, disec isoamide boron. So we write it as Si2BH, and the structure is like this. Okay, so that it will stop at the this one step. So it can react like this. So suppose I am using this R2 as this Si A2. Then next step we will introduce H2O2 in base, so that we will get this OH and H. One thing to notice here is that you have a ene, that is double bond associated with the hydroxyl group. Okay, so this is called enol. Huh? So enol can show tautomerism. Tautomerism. How the tautomerism will take place? So this proton, so this alkene will take this proton, hmm, right? And this oxygen lone pair, it will come here. So this is something rearrangement of atoms so that it will generate this one. So this is the keto form, and this one will be much more stable, the keto form, compared to enol. Okay, so this is one case where this hydroboration oxidation reaction with the alkyne actually forms the keto, not the enol form. So you have to keep in mind. Now let us move further. So addition of water in presence of acid or mercury to salts. Okay, so you have already had this kind of reaction in alkene part. So we are trying to explore same thing with the alkyne. So this is one propene, right? So we're adding water here in presence of HgSO4 and acid H2SO4 to keep the anion same, and we'll end up with CH3 COH, then CH2. So this is similar to the oxymercuration demercuration reaction. So you will get the hydroxo at the more substituted position, and as this is a enol form, so it will tautomerize. So I should keep the equilibration arrow. It will tautomerize to the keto form. Okay, this will be the product. Now to talk of other reactions, catalytic nitrogenation. This is also similar to alkene reaction. So you have the alkyne, and if you introduce to hydrogen over palladium and charcoal, so you will have a scene addition. Both the proton will come in the same side. But now, what is the problem is that it will not stop here. Okay, cannot be isolated. You cannot isolate this one. So again, it will go further and further, and you will end up with the alkane. So basically, you can see it is of no use. Hmm. So to stop this reaction at this alkene level, you have to control the hydrogenation. Okay, so that you can reduce the reactivity of your catalyst. Reduce reactivity of catalyst. How this is done? So there is a specific reaction that is called Lindlar catalyst. Okay, called Lindlar's catalyst. Hmm. So it is basically palladium charcoal, not charcoal actually, calcium carbonate is the support, and that is poisoned by by BaSO4 or lead sulfide. Okay, something like this. So that is the way you can reduce the reactivity of your catalyst, and so that it can stop at the alkene level. So use this H2 EdCaCO3, then we'll get exclusively the alkene product. Okay. Now this was all about the syn addition. What about trans addition? If you need something, for your synthesis purpose, you need the trans product. So conversion to transalkene. How can you do it? So you use sodium, liquid, ammonia. And this is done in very low temperature actually. So you use 2 equivalent of ammonia as 2 equivalent of NH3. Okay, you have to use liquid NH3 as the medium also, and very low temperature such as -78, and you will get the trans product. Okay, now there is always one concern regarding the acidity of terminal alkynes. So why we are concerned for the acidity? Because you see that R C C H. So this triple bond is very electron rich, more S character. So it always generates some partial positive charge on the proton. Okay, so this gets acidic. So it can take part in some acid-base reactions. So we had the pK value of alkynes. So pK of this proton was around 25. So let us look into some of the uh, acid-base reactions. If you react this molecule with sodium hydroxide, okay, so what is the purpose here? Which is the base? You have the acidic proton here. Then first it will abstract it and will generate a negative charge here. So I'll write the product first, minus plus H2O, and this will be stabilized by Na plus, right? Now you have to see it is feasible or not. Okay, so this will be a equilibrium. The pK for H2O is around 16, and for this one pK is 25. So we studied in the acid base class that to uh, get the idea some reaction is feasible or not, or which side it should be going, the forward or the reverse side. You need to get the idea about the equilibrium constant. So K equilibrium is nothing but 10 to the power pk of your species that is on the forward side and the backward. So more likely it will be pk of the conjugate acid minus the acid from where it's starting. So let me just compare it. We are getting 10 to the power minus 9. So it is very, very low. So what we can think that the reaction will be mostly favored in the backside. So this reaction is not favorable actually. Comparatively, so this is case 1. Case 2, if you use some other base, in this case H3 C C C8 plus NaNH2. In this case, what will happen? The same thing. It will extract the proton and the minus charge will be generated, and you will have equilibrium here. You get the anion plus NH3. Now you compare. In this case, pK will be 35, as we know from our previous knowledge, and for the alkyne it will be 25. So that your K equilibrium comes 10 to the power 35 minus 25, that is 10 to the power 10. So this is very much feasible, right? Okay, so this will be go in the forward directions. Now, as this is stable, okay, now you can introduce any of the electrophile here, so that it will go and attack, and you can get your product. Okay, so this reaction is very important, as what you can see here, you are forming an additional bond. Okay, so CC bond forming reactions are always important. This you can, this is a great idea to increase the carbon numbers, or increase the chain length if you do the synthetic chemistry. Okay, now one thing we need to discuss is, in case of multiple, or what to say, so suppose you have some target molecule which is very big, or it has some certain functional groups or connectivity. So before starting the synthesis of this unknown compound, you need to know that how you can get to that compound. Okay, so you need to know number of steps, which reactions you will do, what conditions is required. So for this thing, you can do one pre-hand uh, you know exercise which is called retrosynthesis. So this is called Retrosynthesis. Retro means going back. Okay. So let me give you one example. Your target product is this one. Okay. So this is C3XC. Okay. Now you need to know how you can synthesize this product. So what you really will do is that this is just to help you, for the synthesis process. So first you draw your end product. So uh, seeing this molecule, what you can understand is that if you start with your previous reaction knowledge, if you start with an alkyne and do some syn addition of hydrogen, so you can get to this point, right? So this is the retrosynthesis arrow. Okay, it will go back in previous steps. So if you take this one and do H2 with Lindler catalyst, you will have cis hydrogenation that will give you this product. Okay, now how can we synthesize this one? So basically you see that if you break this bond, okay, so how you can break this bond is such that you can use some NH2 with electrophile, hmm, that is ethyl bromide. Okay, so you know that with sodium amide, you can easily deprotonate this hydrogen. Okay, so that your acetylide anion will be stable, and then it can react to this electrophile and give you the product. Okay, similarly, one more equivalent will give you the more primary product. See, see, this is your starting material. So this is your product. This is your starting material. So this is how, using your reaction knowledge, you can design a reaction pathway for a certain or particular product. Right? This is called retrosynthesis. So there are some particular terms that are used for this retrosynthesis. So this is called synthetic equivalence, and this is also called synthetic equivalent AC. And apart from that, if you hypothetically break this bond, you can have something like this: negative charge and some positive charge, uh, hypothetically. So these are called synthon, SN. So synthetic equivalents are real compound, or synthons are hypothetical, right? Okay. So a starting material can lead to your product in a different way. Hmm. You have number of ways, number of routes, maybe Some route you will have 10 steps, some route you will have 15, or some route you have 5 steps. So it will lead to the product. But most viable will be one will be economical, second will be more yield, hmm, third will be purity, okay, less number of steps. That is coming into the economical part, so you don't need this. So these are the points that you have to consider for most possible pattern, right? So we have discussed the recap of this class, and then we can go to some of the question practice. So just a second. Yeah. Okay, so let us go with some question practice. So these were from the um, free assignment part, non-graded assignment. So in the first question, which of the following is the best synthesis of 1122 tetra bromo propane? Okay, so you have the previous idea that let me just write it. Propane. Okay, so now you can see that if you have alkane here, if you have alkane, you can only have one bromonium ion possible. So it will lead to just dibromo compound. So it will lead to dibromo, not the tetrabromo product. Only when you are having alkyne, that time it is possible that you are having the tetrabromo compound. So in this case, so this is the second one. If you are adding Br2, the first one bromonium ion will form, will have this compound. Now you can have another bromonium ion formation, so that it can lead to this compound, right? Okay, so it should be anti, because of the bromonium ion state. This will be anti, and then you will have the tetrabromo compound. So this will be your right answer. So HBr peroxide, one side will be H, one side will be Br, so you don't have both side bromo, Second question is that what is the reagent to perform the following transformation? So you see that this it looks like just a second, it is not working. Maybe there is some problem. Let us wait for a few minutes. Yeah, now it is okay. So you can clearly see that here two protons had been added in the syn way or the cis addition. So this is stopping in the alkene, just one step, not going to the alkane. So basically, Lindlar catalyst has to be used and it has to be catalytic hydrogenation. So this one will be right answer. Okay, move to the next question. So alkene RCCH is given. It is written which of the following bases will drive the reaction towards the product of the reaction. Hmm? This is the acetylide, uh, not acetylide. Sorry. Yeah. Uh, so when you consider this one, you have RCCH plus base will have RCC minus plus base H. You have to consider the pK. This is 25 and this pK will vary. Okay, so for this one, the conjugate base will be like we have CH3 here and it will be pK is 50, I think. Yes, okay, 50. NaNH2 will be NH3, pK will be 35. For this one, it will also form a amine, pK 35, and both OH minus, so it will be H2O, pK equal to 16. So you can see for 1, 2, and 5, the pK value is more than your acetylene or the alkyne pK. Okay, so this will be much more favorable, while this two will not be favorable. So 1, 2, and 5, this can abstract the proton from the acetylene. Okay, so 1, 2, and 5, this option will be right. Okay, I guess you have understand. Then the next question is what is the major product of the reaction? Okay, with O3 and dimethyl sulfide. So how we will draw. Okay, this will be your the intermediate. Now the bond will break so that you will have one aldehyde in this case and one ketone in this case, and you have one, two, three, four carbon gap. So you have one, two, three, four carbon gap. One side is aldehyde, one side is ketone. So this one will be the right answer. The right answer is one. Move to the next question. So this is a plant. So something is produced when one equivalent of HBr is added to one hexane. And let us draw it. One hexane. Then we are adding HBr. So as an electron rich compound, so it will come and attack the proton and bromine minus will be generated. Now you have to check this carbocation or this carbocation, which one will be stable. So as per my knowledge, I think this one will be stable because it has additional methyl or methylene group that can donate the electron. Okay, this has plus I effect that can donate the electron and stabilize the carbocation. So this one will be stable, and then bromo will come, so that will have the product. So this is what 2 bromo hexene. So this one will be right answer, 2 bromo 1 hexene. Let us move to the next question. So what is the major product of the reaction below? Okay, let us draw it as HBr. Now similar thing will go generate the positive charge, and this one will be much more stable, right? And bromine minus will come, and you will have this compound here. Now you have excess HBr. So again HBr is there, it will attack. Hmm. Now you will have a carbocation here again, and then bromine minus come, and you will have. So I'm not showing the other possibility or the minor product. I'm just drawing the major product. So what is matching here? This one. Yes. So 2 is the right option. Go to the next question. In the reaction of an alkene with OSO4, what is the relative orientation of two OH group in the final product? So they are seen, right? So you already discussed, if you have an alkene and you have OSO4, so they will be like this. They are seen. Same side they will bend. They are seen to each other. Next question. What is the reagent to perform the following transformation? So you know it is a syn addition and it is stopping only at the alkene. So you know what is the reagent, that is palladium carbon with Lindlar catalyst. Now what is the major product from the following reaction? Okay. So HgSO4, H2SO4, H2O. We have already discussed this one. Let us draw it. So you will have the water at the more substituted position, but as this is a enol, it can tautomerize to this keto form. This is enol form. Okay, so this one will be the right answer. So which is the one? This one. Let us go to next question. Write the major products of the reaction. Okay. First thing is BH3 THF. What will happen here? BH2, then H. So this one will be a concerted addition actually, right? So what you get from here, okay? And now you do the workup and you will get OH this. Now, uh, as this is a chain addition, okay, what it can do based on the relative geometry of this isopropyl group, so it can form two isomer, okay, either this one or the other one. So this one will be a enantiomer. Okay, so this is called actually, this place is called stereogenic center. Hmm. You see here you have a double bond, but the three substituents are different on three sides. So if you convert this sp2 to sp3 carbon, then there will be four different groups. So this will be chiral. So it will be present as racemic mixture of both, okay, 50-50, but you will have both 1 and 2. Next is select the incorrect option, the first step hydroboration in question 5. So the last question, first step, okay, is a concerted addition. This is right. A chain addition of H2 and BH2. This is also right. Proceeds with the formation of triangular intermediate. This is not right, right? This is a not triangle. This is a square type or rectangular type intermediate, not triangle. So this is wrong. And the transition set has a four-member tree. Yes, yes, this is a four-member tree. This one will be the incorrect one. What is the major product of the reaction? You know, so they have used on oxidizing condition. Okay, so if any aldehyde is getting formed here, that will be converted to the acid. So in this case, okay, this part will have the ketone form, and this part will have the aldehyde form, but it will convert to acid. So acid part will have one, two, three, four carbon. This part will have one, two, three, four, five carbon. So let us see. Uh, 1, 2, 3, 4, 5. 1, 2, 3, 4. So here it is aldehyde. It is not an option. This one, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so this one is converted to acid, so this will be the right option. This one. Okay. Now move to next question. Select the incorrect statement. Terminal alkynes are more acidic when compared with alkynes. Alkynes are more reactive than alkenes. Alkenes are less reactive than alkenes, and terminal alkynes are more acidic when compared with alkenes. So let us just write that uh, CCH, this pKa is 35. Okay, R, so alkene pKa is, let me check once, is 40. This is not 35, this is 25. Okay, so you can see the pK value is less for the alkyne than your alkene. So this is much more acidic. So diamine alkanes are more acidic. It is right, and alkynes are less reactive than alkenes. Yes, this is true because uh, this is your alkyne, this is your alkene. So somehow this delta G double dagger for the transition state is higher for alkyne. So they are less reactive. Sorry, right? So this is also right comment. Terminal alkynes are more acidic when compared to alkenes. Yes, actually 1 and 4 are same thing. So alkynes are more reactive than alkenes. This will be the wrong comment. So this is the right option. Okay, as alkynes are much more stable, so their activation energy is higher, so they are less reactive. Now rank the following in the order of stability. So here 4 will be much more benzylic carbocation, so this can take part in resonance, right? Therefore you have the 3-degree carbocation. So what I told you that a carbocation that is present on sp3 is stabler, like more stable than when it is present on some other, sp2 or sp carbon is not possible, sp2, because of the relative s character and the electronegativity of the carbon atom. So generally the sp3 carbon will come at first, so 4, 2, and then 1, and at the end it will be 3 stability. So what is the option? 4, 2, 1, and 3. Yes, this one. Now the next will be what is the final product of the reaction sequence below. So you are having an substituted alkyne. So you are giving sodium with liquid ammonia. So this will give you the trans hydrogenation. So first step it will come. This will be your first step, and second you will have Br2 CCl4 and anti-addition, So then you will have something like this. So let me represent it. Okay, these two bromo will be anti to each other. For going through bromonium intermediate reaction, so the reaction has to go in the anti pathway. So which one will be the right answer here? You can see here it is seen, so not possible. Here also it is seen, not possible. Here only the first step has been done, second step is not, so not possible. Here you can see these are in anti position, so these are the right option. So two only will be the right option. So with that, I think today we have covered the recap of the week 6 classes and we have discussed many of the questions. And so I'll stop it here. And if you have any questions, you can reach out to me at any case. And okay, all the best for the course. Okay, thank you.